Morning, everyone. Welcome to 3D Vision. I'm Xiaoxiao from Nanjing University. Let me briefly introduce myself. I, uh, I obtained my PhD degree from the Hong Kong University. In the past nearly 10 years, I study 3D Vision. Um, Maybe it can call it spatial intelligence. Yeah, my goal is to develop algorithms that can convert images and videos into 3D representations. Yeah, in this course, I will briefly to introduce how the computer perceive, reconstruct, understand, and eventually interact with the 3D dimensional world. Yeah. Uh, Currently, the AGI, the idea is quite popular, yeah, because every day we we will use like Claude, DeepSeek, or GPT every day, yeah. So uh, the development of the, the GPT maybe let us to have an idea that the AGI is quite close, yeah. But generally, there are two broad paths toward artificial general intelligence. The first is to learn from the human experience, especially language and the other human-generated data. This path mainly develop cognitive skills such as reasoning and decision making. The second one may be the to learn through the interaction with the real world, like the robots and many skills that require the physical skills like perception, control, dynamics, navigation, and manipulation. Yeah, we believe that these two paths need to come together to robots can help human beings do many works in the reality. So the first question is that what's the spatial intelligence? Maybe we can call it physical AI. Yeah. The Feifei Li from the World Lab introduced spatial intelligence that it's the ability that to make AI can model the world and reason about objects, places, and events in the 3D space and time. Yeah. In this example, singing tells us that the cat has pushed the cup. Reasoning predicts that the cup may fall and break. Acting means that moving quickly enough to catch it. So a physical agent must connect all three stages to make the agent can perceive and work in the real 3D world. This figure from the NVIDIA, yeah, this figure places the physical AI beyond the perceptual, generative, and agentic AI. Yeah, the the NVIDIA believes that the physical AI will be the modern development of the future. Yeah. So a model can recognize an object, generate an image, or plan a sequence of actions. But physical intelligence requires these abilities to be grounded in the real world. Yeah. The system must understand geometry, motion, physical constraint, and the consequence of actions. Yeah. In this lecture, I will briefly to discuss why 3D vision matters and review the organization and expectation of the 3D vision. And we will revisit the basic goal and challenges of the 3D vision. So let us begin with a simple observation. 3D is everywhere, but one question is, what's the 3D? Yeah. Every day, our human beings live in a 3D world. We can use our eyes, our nose, and our hand to perceive the world. But for the computer, what's the 3D? Yeah. For example, in this image, we can capture a room use our phones. Yeah, we can capture a video or take a picture. But the image and the video is it has a only fixed viewpoint. If we want to take a free viewpoint in the captured environment, how can we to achieve this? So this question is a fundamental problem in the 3D vision is that how can we use images and videos to reconstruct a 3D representation? Let us to interact with that and take any viewpoint in that. Another application is that we can create some digital 3D world, yeah, like a room and many size to make a design for our room. Yeah, this is quite useful in the inter, inter, interior design, virtual property tours, construction, and culture preservation, and many other applications. Yeah, this important point is that the output is not just an image or video; it's a representation of a space. Augmented reality takes this one step further, like digital content must be placed consistently within the physical environment. Yeah, you can use the VR glasses to view and perceive the digital 3D world. Yeah, to make the virtual buildings in the example appear stable on the table, the system must understand like camera motion, surfaces scale, and occlusion. Yeah. Reality, virtual reality creates the complementary experience. Instead of placing the virtual object in the real world, it places the user in a virtual world. Yeah, to support the natural movement, the system must to track the user and render the scene correctly from a continuously changing viewpoint. 3D perception is also important for the robots. Yeah, a robot must to determine where objects are, like how they are oriented, which areas are free, and how its actions will change the scene. Simulations of environments allow us to train and evaluate these abilities before developing a system in the real world. Like the self-driving cars also need the ability of 3D vision. Yeah, in this figure, the colored points here represented a reconstructed structure 3D-dimensional environment. The vehicle must to estimate the geometry and the motion of the roads, cars, uh, pedestrians, and other objects in order to plan safely. So 3D vision is already used across perception robots, graphics, augmented, and virtual reality. Its importance will continue to grow as the AI moves from understanding digital content towards operating in the physical environment. Yeah. So why do we focus on 3D? Maybe the short answer is that our world is three-dimensional. Yeah. Images are only the projections of the world. If we want an AI system to reason about like distance, size, free space, contact, or other physical interaction, it needs some form of 3D understanding. Yeah. In fact, the research community has responded with a huge increase in activity. Like the CVPR 2025 received more than 13,000 submissions and accepted nearly 3,000 papers. So, in fact, no one can follow every paper anymore. So it's increasingly important to understand and the underlying ideas rather than memorize individual methods. So this is a chart shows that the primary topic of CVPR papers in 2020. In that time, recognition and deep learning are dominant, while topics such as 3D scene understanding and reconstruction form an important part of the conference. Yeah. At that point, 3D still a topic among many other hot points. But by 2023, like the topics like 3D formative view images and sensors had moved to the top of the topic. Yeah, image and video synthesis also growing rapidly. This reflects a broader shift from recognizing content in the images toward to reconstruct the 3D scene or generate complete visual worlds. The 2025 the chart shows that this trend has continued. Topics related to the multi-view 3D synthesis and embodied AI or robots occupied a major part of the conference. Yeah, actually, uh, more than half of the papers are related with the 3D vision. So let us start from the broader goal of the computer vision. Yeah, the camera measures light. So the goal of the computer vision is to convert those measurements into meaning. That meaning may be semantic, such as recognizing an object, or geometric, such as estimating its position, shape, and motion. Yeah. A useful summary is that like the three W's: what, who, and where. What refers to recognition and segmentation. Who includes people, entities, and poses. Where refers to the geometry, like the spatial arrangement of objects and the structure of the scene. 3D vision is especially concerned with the third question. Yeah. So many applications related to 3D vision and the biological vision remind us how important the problem is. Yeah, a very large fraction of the human brain is involved with the visual information. Right? Humans solve many visual tasks, but the apparent is that the result of the the complex biological system. So, an interesting question is that why, as human beings, even many animals have two eyes? Yeah, this question is interesting and also very important. Yeah, actually, the reason is that uh, our as human beings and animals have two eyes because we actually need the stereo depth perception. Only two eyes can lead to accurate stereo depth perceptions. Yeah, because the two eyes observe the world from slightly different positions, so the images for the two eyes are different, and us and the brain use these differences together with other cues to estimate the depth. Geometrically, the point observed in an image corresponds to a ray in the 3D dimensional. Yeah. So a second observation gives us another ray. Yeah. So we know two non-parallel lines can interact and it will give us a point. So our people have two eyes, so we can use the two ray to decide which point in the surface. So this is the basic idea of the triangulation, and the triangulation will be the basic idea in the 3D vision. Another familiar topic is the computer graphics. Yeah, but the computer vision and computer graphics solve the inverse problems. Yeah, graphics start with a 3D scene, geometry, materials, lighting, and cameras, and we will use some algorithm to lift the 3D created 3D into image. But 3D vision starts with another direction. Yeah, vision starts with like images and many images in the scene, and to segment it and perceive it and lift it into 3D. So computer vision and the computer graphics is the inverse problems. Yeah, why visual perception is hard, like or 3D vision is hard? Yeah, because for us human, yeah, we can quite easy to look at the scene and to understand the objects and actions. But for computer, the input is not the pixels, but actually it's the numbers. Yeah. On the left, we can see a street, buildings, and people and depths. But on the right, the computer initially to see the matrix of the values. So the gap between the two descriptions is a fundamental challenge for the computer vision. Yeah, for the 3D vision, a major challenge between the 3D vision and 2D vision is that the images are the 2D projection of the 3D world. Yeah. Actually, we can see the four diagrams. Yeah. It's different, but if we use a camera to capture the four cases, the image will be the same. Yeah. So the problem is that called ambiguity. Yeah. So the image is a 2D dimensional projection of the 3D world, but many different combinations of a shape illumination can create a exactly same image. So for the computer, it's quite hard to use just an 2D image to guess what the 3D world is. We can see an interesting experiment.
Does our brain construct its own version of reality, one that does not always match up with the physical universe? Check me out, for example. I am the same size here as I am over here, but over here I look much larger. No, it's not a cheap video trick, it's a trick on your brain. Here's what you're seeing. The me over here is indeed projecting a smaller image onto your retina, the region of light detecting cells at the back of your eye. All else being equal, smaller images mean smaller things. Here, I'm in no danger of hitting my head on the ceiling. But over here, I am ducking. Ceilings are useful visual landmarks for judging size. Of course, you're making these size estimates based on the assumption that this room is ordinary and box-shaped. You assume the back wall is perpendicular to the line of sight, so the two versions of me are the same distance away. You're also assuming that the floor and ceiling are level and parallel. But as you've probably guessed, this isn't the case, and the room isn't box-shaped at all. It's trapezoidal. The back left corner of the room is much farther away than the right. Since I'm farther away over here, my image is smaller, although I'm definitely not. The ceiling cue is also misleading. The floor actually slants upward and the ceiling downward from left to right, making my head much closer to the ceiling when I'm over here. Why couldn't you see these things and adjust your size estimates? The room's features have been cleverly distorted to be consistent with a rectangular shape. The checkerboard pattern on the floor gets finer grained toward the right, so that the same number of pattern elements fit in a shorter distance. The windows are resized and shaped to match the trapezoidal back wall. Your narrow angle of view from the front of the room blocks the cues that would reveal the room's true shape. And of course, we easily believe in a box shape because that's the shape rooms normally are. This clever setup is called the Ames illusion. American ophthalmologist Adelbert Ames Jr. devised it in 1934 and built a physical example the following year. For Scientific Americans,
So the image room illusion demonstrates how the strongly perception depends on the assumption of the geometry. Yeah, because every day we perceive the room should be regular, but in this case, the room is not regular. So we can perceive, we can wrongly perceive that the human size will be different in the different viewpoint. Yeah. So one assumption is that our brain accepts the interpretation, causing people at different depths to appear the different in size. But we know the human being cannot change its size. Yeah. Another challenge for the 3D vision is that the viewpoint variation. Yeah. So objects may look very different when the viewpoint changes. Yeah. But for the 3D vision, we need to solve a problem yet to find the correspondence between the images. Yeah. The three images contain the same character, yeah, but it creates within different shading and the proportions. Yeah. So a robust 3D vision system must to recognize the underlying object despite these changes. Another challenge for 3D vision is the deformation. Yeah. The very important problem of the 3D vision is to reconstruct like human being, the human body. As we know, the human is non-rigid object. Yeah. So the non-rigid object will introduce deformation, like in the case a running horse changes its shape and the relative positions uh, from from frame to another frame, and the 3D vision system has to distinguish it should be a same shape and to know its rigid shape deformation and to reconstruct it into the 3D representation. Another challenge is the occlusion. Yeah, occlusion had part of the scene. Yeah, in this image, the person is difficult to detect because the body is partially hidden. Yeah, illumination is another major source of variation. Yeah, in many cases, we need to use some image may be captured in the night to create a 3D world, but many familiar objects will become almost invisible. Yeah, the pixel intensity is not a direct measurement of a shape. It depends on the illumination, material geometry, and camera responses. Yeah. When the appearance is different, the captured image will be also different, right? So in a more natural illumination, the scene becomes easy to recognize. Yeah? Comparing this image with the previous two images shows that why the appearance alone is unreliable. Yeah, we need to model the separate stable scene properties from changing image conditions. Lighting direction even change our perception of the shape. The same geometry may appear convex or concave, developing on where we believe the light is coming from. This ambiguity motivates methods such as shape from shading or the photometric stereo. Also, motion creates blur, deformation, and rapidly changing appearance. At the same time, the motion is also a valuable source of information. By tracking how image content changes over time, we can estimate object motion, camera motion, and sometimes 3D structure. Another challenge is local ambiguity. Yeah? A small or blurred local region may be impossible to interpret on its own. In this image, local evidence does not clearly tell us what the object or action is. But if we see a more clear image, we can recognize actually the human is not calling a phone, but it's take another different object. Yeah. Also, the 3D vision study a problem that to distinguish objects within a same category. Yeah. Because like we see the class, the chair class in a famous data set like the shape night. Yeah. So there will be more than 1,000 classes of the chair. We also need to find out the difference of the chairs. Finally, the word contains a huge number of categories, depending on how finely we define them. Yeah, there may be tens of thousands of the visual relevant object types. A practical system must therefore learn scalable representation rather than rely on one manually designed rule for each object. The fundamentals of the 3D vision were developed long before computers. Yeah? Da Vinci studied perspective. Lambert formalized the photometry, and Gauss developed the least square estimation. Yeah? Modern 3D vision combines the same ingredients: projection, light, numerical optimization, and multiple viewpoints. Da Vinci described the perspective using a transparent sheet of glass placed between the observer and the scene. Rays from the scene pass through the image plane and meet at the eye. This is remarkable close to the pinhole camera model that we still use today. A three-dimensional scene is projected onto a two-dimensional plane through ray of light. The daguerreotype, introduced publicly in the 1839, was the first widely available photometric process. A silver-coated copper plate was made light-sensitive, exposed, and developed using vapor. This machine can transform the visual observation into a producible measurement and can provide the data used by computer vision. The Great Trigonometrical Survey of the India illustrates large-scale geometric estimation before the digital computers. In that day, the human can connect many measurements through a network of triangles and repeatedly to adjust the estimate to reduce inconsistency. Conceptually, this resembles modern bundle adjustment, where many camera poses and 3D points are jointly optimized. So the timeline summarizes several waves of 3D vision. Early work focused on the block worlds and edge-based models. The 1970s and early 1980s developed low-level cues such as stereo, optic flow, and shading. The 1990s brought dense reconstruction and the optimization. The 2010s emphasize features and large-scale structure from motion, followed by deep learning, large data size, and in the 1957, Gilbert demonstrated an analog system for stereo image correlation. This work led to instruments such as the Rosenwald stereomet, which supported to elevation map production from the aerial photographs. The stereo vision was therefore useful for practical 3D measurement and before the modern digital vision systems. Larry Roberts' block words research was an early attempt at machine understanding. This system extracts image edges and interpolates their topological arrangement as the projection of a 3D object. The key conceptual shift was to treat an image as evidence about a three-dimensional science scene rather than a purely two-dimensional pattern. The 1966 MIT Summer Vision Project famously underestimates the difficulty of computer vision. The project suggests that students could solve a large part of vision during one summer, focusing mainly on a simple block word. Its failure became an important lesson. Visual perception requires much more than a few careful design rules. And the MIT copy demo connect vision, planning a robot manipulation. This system observed a structure made of blocks recovered its arrangement and asked a robot to build a copy. This was an early perception to action pipeline. Yeah. However, unreliable low-level edge detection limited to the system and motivated deeper work of the basic visual processing. Shape from shading tries to recover 3D shape from the brightness variation in a single image. Early formulations assumed that the Lambert reflections and consistent albedo, then use a smoothness constraint to make the ill-posed problem solvable. The idea is powerful, but its accuracy depends strongly on the lighting and the material assumption. The intrinsic image framework proposes decomposition and observed image into underlying components such as the reflectance and shading. Instead of treating pixel colors as a single property, it asks which parts come from the object's material and which parts come from the illumination. This decomposition remains relevant in the inverse rendering and scene editing. For the metric stereo, use several images captured from the same viewpoint on different lighting conditions. With at least 3 known lighting directions, we can estimate the surface orientation at each pixel because the camera does not move. So difference between the images mainly reveal how the surface responds to light. And the essential metrics provide a compact representation of the calibrated two-view geometry. A point in one image maps to an line in another image, reducing a two-dimensional correspondence search to one-dimensional search. It also allows relative camera motion to be estimated from matched image points. Early binocular stereo methods searched for corresponding points along the line. Dynamic programming introduced ordering and smoothness constraint along each row, helping resolve some ambiguity matches. However, optimizing rows independently often produce striking artifacts and inconsistent results. And optic flow technology was introduced in nearly 40 years ago. The optic flow describes the apparent motion of image content between frames. Yeah. That time, a method called Horn shrunk estimate a depth motion vector for every pixel using brightness consistency and the global smoothness. Optic flow became a fundamental tool for motion analysis, tracking video understanding, and later learning-based vision. Path-based models represent a complex object as a combination of simpler components. Examples include pictorial structures, generalized cylinders, and other shapes. This gives us a compact representation that can express both the shape of each part and the relationship between the parts. Magic Cube's algorithm converts an implicit volumetric representation into a surface mesh. It examines each voxel cells, determine how the surface intersects the cell, and generates polygons using a configuration table. The algorithm can move through the volume. It remains widely used in metal imaging, 3D scanning, and neural reconstruction. Actually, nearly 40 years ago, the community had already to try to develop the self-driving cars. Yeah, maybe it can be called the most early is the self-driving car called the Waymo. Yeah, the Waymo developed by the Dinkmanis was an important early self-driving vehicle. It used dynamic vision to for the control and was demonstrated at speeds up to 36 kilometers per hour. Yeah, this work shows that the visual perception could support real-time vehicle control using the computer resources even available in the 1980s. Owen introduced a learning-based approach to the autonomous driving. Yeah, it's a fully connected neural network introduced in the 1988. This network mapped the forward-looking road images directly to a steering direction. Although the network was very small by the modern standards, it was tested on multiple road types and demonstrated that the driving behavior could be learned from the visual data. Yeah. So actually, even 40 years ago, the researchers have already to try the neural network for the self-driving application. Yeah. Nearly 30 years ago, like in the 1992, most important idea was developed in that day, like the structure from motion. Yeah. The problem of structure motion is to estimate 3D structures from 2D images in a sequence. Yeah. Structure motion, or call it SFM, jointly estimate camera motions and the 3D structure of a static scene from a sequence of images. Yeah. It can tell us the camera, the position of the camera, and tell us the location of each captured image in the 3D world. So we can use calibrated images to reconstruct dense 3D point from the images. ICP, or call it iterative closed point, is another famous idea developed in the 1992. Yeah, it can align two different point clouds. In currently, maybe we are familiar with the Kinect, the depth sensor. Yeah, the depth sensor can provide us different scans of a room. Yeah, but in many cases we don't know the exact location of each scan, so we can use ICP algorithm to align the different two 3D point cloud into a merged one. Another important idea is the volumetric fusion. Yeah, volumetric fusion combines multiple surface measurement into a common volume, typically by averaging signed distance values. Yeah, measurements from different viewpoints reinforce one another and reduce noise. After fusion, a mesh can be extracted from the implicit surface. Yeah, the idea becomes very hot to the real-time RGBD reconstruction system. Yeah. The multi view stereo algorithm should be the most important in currently, yeah, because multi view stereo provide us a fundamental system to use images or videos to reconstruct 3D geometry. Yeah, the level side formulation represent the surface implicitly. Yeah, can handle changes in topology and visibility. And graph card stereo was introduced in the 1998. Yeah, graph card stereo formulates the correspondence as a global inference in a Markov random field. Correspondent with the prior independent scanline method, graph cards can allow information to propagate across the image and produce more coherent depth maps. The 3D morphable model represents take a face as a linear combination of later scan example. In that case, that should be the most popular, the like the digital human used in the movie. Yeah, this technology can use like scans of the laser and to reconstruct a digital face of the human being. So we can use the digital face to in movies and games. And the face is not static; it can be morphable. Yeah. So by fitting the model to a single photograph, the method could estimate a plausible 3D face and modify its shape, pose, and appearance. So the results was especially quite impressive for the computing and data available in the 1999. Another popular idea like the SIFT, yeah, the SIFT can detect and describe distinguished local image features that are robust to changes in scale and rotation. Reliable local correspondence enable the image's staging, object recognition, motion estimation, and 3D reconstruction. So the SIFT became a key building block uh, in the classical structural motion pipeline. Also, it has a small story behind the development of SIFT. Yeah, the SIFT paper was rejected many times before it be a publication, but today we know that the SIFT will be the quite fundamental idea in the 3D vision, even many vision tasks. In 2006, the photo tourism idea is popular in the with the emergence of uh, the phones, yeah, and the cameras and the digital cameras, people want to create a 3D world from the internet photos, yeah, like the quite initial idea of the Google Maps, yeah. People would like to see the 3D thing in the is that okay? Yeah, without to go there on site. Yeah. So the photo tourism demonstrates large-scale 3D reconstruction from unordered internet photos because the photos may be captured in different time. Even like some photos are captured in the spring and some photos captured in the winter. Yeah. So the technology is very impressive and challenging. Yeah. And then Microsoft first developed a robust system that can to use the captured by different people and capturing the different time and capturing different positions and use all the massive of internet images to create a 3D world to enable the user to perceive and look the 3D world in any free viewpoint. And in the 2007, PMVM, the patch-based Matterview stereo, may be the famous 3D reconstruction method was developed. Yeah, it extended spatial reconstruction into dense geometry. Instead of matching individual pixels, it grew small oriented surface patches and verified them across multiple views. This produced a very robust reconstruction of objects and scenes at different scales and became an important classical MVS method. In 2007, a very famous paper called Building Roma in a Day was developed. In this method, the researchers using the images obtained in the internet and to use thousands of internet images to reconstruct the 3D shape of the Roma. Yeah, and the 3D reconstruction of the landmarks and the cities from the unordered internet photo images. In 2011, a famous the Kinect sensor called Kinect was developed. Yeah, the Microsoft launched the sensor uh, in 2011 because in that day the idea of VR is very popular. Yeah, but we only use images like cameras to reconstruct a 3D shape is quite a challenge and cannot be real time. So that day, the Microsoft launched the product called Kinect. It can use like laser light to get the 3D shape of the 3D shape like a people and the object. Yeah. So Kinect made active depth sensing. It combined a depth sensor with machine learning methods for real-time human pose estimation. Although the Kinect did not remain a permanent consumer product, its low cost and real-time depth output had a major impact on robots, human-computer interaction, and 3D vision research. Even today, many robots also will use the Kinect sensor to capture the 3D vision, 3D world, and to plan and to escape obstacles. When I was undergraduate, yeah, I was shocked by a quite famous word called deepfakes. Yeah, that should be the uh, deep the AI synthesis technology was wide known by many people. Yeah, the deepfakes technology combines the model-based face alignment with deep neural networks. Yeah, I also remember the video in that day that the technology fakes very many famous people and quite mimic. Yeah, and in that day, many people in the world even discuss how to distinguish the faked people or with the real people. Around the same time, researchers began to building a holistic 3D understanding system rather than detecting individual objects independently. This system jointly estimates roads, vehicles, scene geometry, and spatial relationships. The example here focuses on traffic scenes observed from a moving platform. Yeah. Also, the same idea expanded to the indoor and outdoor environments. Data sets such as the sun, RGBD, and Kitty make it possible to evaluate scene classification, semantic segmentation, room layout estimation, and 3D object detection. Data sets became an important driver of progress because they define common tasks and measurable benchmarks. Also, modern 3D scanning technology can create highly accurate digital uh, objects. In this example, a team led by Paul scanned President Obama for a detailed 3D portrait displayed by here. Such systems combine careful capture, geometry, reconstruction, appearance modeling, and sometimes 3D printing. By 2018, models for human shape and pose had become much more mature. Parametric representation such as simple will be quite familiar in that day. The simple models describe the body shape, pose, and pose development deformation with a quite compact set of parameters. Learning-based systems can regress these parameters from RGB images even without a depth sensor. Between roughly 8016 to 8080, deep learning expanded from two-dimensional outputs to native 3D representations. Network began predicting pre, predicting voxels, point clouds, meshes, and implicit functions. They could infer 3D structure from even a single image and increasingly model geometry together with material lighting and motion. Differentiable rendering connects a 3D representation with image-based supervision. NERF, for example, uses a coordinate-based network to model density and color in a scene, then applies volume rendering to synthesize new views because rendering is differentiable, so the 3D representation can be optimized by converting rendered images with photographs. More recently, 3D generation has become influenced by the larger two-dimensional diffusion models. Here is a work created by the Stable Diffusion model. It calls the score distillation sampling. In this method, you can just send input a text prompt into the system, and the system can create the 3D world, a 3D object, without you to manually create it. So the history has led to a wider range of commercial applications. Let me continue. So here, let me answer the question that what is 3D? 3D actually is a 3D is quite too difficult to interpret. Because like a human being, actually we don't know what the 3D is. So for the computer, how computer to understand what 3D is? So actually, 3D has many representations. In the 3D vision or computer graphics, the community, the same object can be represented by many different representations, like a point cloud, a mesh, a voxel grid, even a parametric surface or an implicit function. So each choice stores different information and supports different algorithms. So the 3D software is much less unified than image software because if we capture an image, we can understand that the image is just an array or a matrix of 2D arrays. But for 3D, we can use different representation to represent it. The first one is that we can use 2.5 dimensional representation. It's called the depth map. The depth map is quite easy to understand. It's not a pure image. It's an image stores the distance between the object and the camera. Here is an example. An image is the depth map is an image that represents how far each pixel is. So usually we just can use one-dimensional image to store the depth values. So in that case, the bright ones means that the pixel is much near from the camera. So because a depth map is a regular two-dimensional array, you can use the standard image processing tools. We can filter it and compute gradients and apply convolutions, like build pyramids and feed it into a convolution network. It can be used as a regular image. Yeah, but the depth map, the values, the pixel values stores the 3D information. We can also associate another surface properties with the same pixels, like the normal map. Yeah, the normal means the orientation of the surface. Yeah, a normal map will store the three-dimensional unit for normal at each visible location. Yeah, so the color is often used to only for visualization because the normal is range from -1 to the +1. Yeah. So the different colors respond to different surface orientation, and depth and normal together can provide a richer local description of a shape, but the representation is still not 3D. The limitation is that a depth map describes only uh, which is visible from one viewpoint. Yeah, so we cannot know the shape of the invisible part because we can only use an image to represent it. So for this reason, the depth map are often called a 2.5 dimensional representation. It's not a 3D representation. Yeah. So the depth map can attach geometrical properties to a two-dimensional image grid. So for the deep learning area, depth map estimation should be the first two topic attract lots of attention in the deep learning area, and many researchers like in 2014, researchers started using like a convolution network to estimate depth map from image. Why research focus on this topic first? Because in that day, convolution networks can only use to process or analyze the 2D images. So the depth map in the formulation is the same with the image. So that day, researchers will use convolution networks to process the image and to produce its depth map. Yeah. So for a long time, the depth map study dominate the CVPR conference or like ECCV conferences. Yeah, because the representation, the 2D representation is quite compatible with the convolution networks. Another representation can be called LiDAR. Yeah, the LiDAR point cloud is also captured by the laser. Yeah, but also we can store the laser values into a 2D image. Yeah, but for the depth map, the depth map should be a dense pixels. Yeah, but for LiDAR map, the LiDAR will be sparse because for a laser, it usually have like hundreds of laser points. Yeah, so you cannot assign uh, assign a value for each pixel in the image. And bird's eye view, or called BV, is another two and a half dimensional representation. Yeah, it provides sensor information onto the ground plane. The BV representation is uh, widely used in the autonomous driving applications. Yeah, because we know the ground can be a projection of the three-dimensional, yeah, and the car only to move on the ground. So why we call the BV representation? Because this representation imagines that if we are a bird, yeah, so we can use a bird viewpoint to see the ground, yeah. So we can to store the cars and the moving objects in the plane, right? So although the autonomous driving is a 3D world, but we can still only store its position in a 2D map. So we can still use convolution network to process uh, the BV representation. Here is a representation. Yeah, this is a 3D reprojection results of the depth map. Yeah, because the depth map stores the distance values, so we can still to lift the distance values into 3D. So we can reconstruct the 3D point from the depth map. Yeah. So the depth map has many benefits. The main benefit is that it's quite compact storage. Yeah. So because although the world is 3D, but we can still use 2D images to store the information, and it's compatible with standard convolution networks. Also, the currently transformers. Yeah. Another important representation is the point cloud, yeah, because how we to perceive the 3D world or we represent the 3D world. Straightforward idea is that you can use lots of points, like million of points to represent the 3D world, yeah, because every shape has its surface. We can sample many points from surface, yeah, so we can use the point cloud to represent the 3D world. But how to get the 3 points? So we can use the Kinect, like just mentioned, the product announced by the Microsoft. Yeah, it's a depth sensor, but we would like to call it is an active depth sensor. It will send in active uh, light sensors into the 3D world, and because we know the light hits a surface, it will be backward, right? So we can calculate its time and calculate its distance between the object and the sensor. So we will use the depth maps obtained from Kinect and lift the 2D dimension 2D depth map into a unified 3D point cloud. Mathematically, a point cloud is a set of points. Yeah. So if we permute their order, the represented shape still remain exactly the same. In code, we commonly to store a point cloud as a n-by-3 array containing x, y, z coordinates. Also, we can enrich a point cloud by attaching a normal to every point. An oriented point cloud can be viewed as a small disk rather than a tiny sphere. So this idea is quite from the Gaussian, yeah, if you know the Gaussian splatting. The Gaussian splatting technology is use a set of Gaussian spheres. Yeah, it's the Gaussian splatting idea may be motivated by uh, uh, the oriented point cloud. But a basic point cloud contains no explicit connectivity. Yeah, because these points might sample one loop, two loops, or from another structures. So from the coordinates alone, we have to infer which samples belong to the same local surface and which points should be connected. So the mesh was developed to uh, to solve the difficulty of the point cloud. A mesh can be easy to understand. Yeah, a mesh has 2 parts, verticals and faces. Yeah, the verticals, the vertex store the position, while the every face stores the indices of the vertices on a polygon. Yeah, triangle faces are the most common and the quite easy to use representation in today. Like if you play games, all the characters and the things are uh, stored as a mesh. Between the mesh, the triangular meshes are widely common used because it's represent object as a side of triangles. And the triangle have many uh, good properties. Yeah. Why the meshes are wide used in today, especially for game and movies, because meshes are excellent for tethering. Yeah. We just introduce a mesh. The mesh is a set of vertices and indices, so it cannot store like colors and appearance. But we can, still to use a technology called tethering to assign the colors or the appearance into the mesh. Yeah, how it works? Yeah, a relatively small set of vertices and faces can define geometry, while a high resolution two-dimensional texture map, we call it texture map. It can store appearance like, or we call it colors. How we to align the two representations? If we know, if you know the function, yeah, we can create a function like a three-dimensional map to 2D dimensional, right? Because for the mesh, we store a point like XYZ. And for a 2D dimensional texture map, we call it a UV image map. Yeah, so we can store a mapping like XYZ to UV. Yeah, so we can link the 3D point and the 2D color. So the mesh and the texture map is quite widely used in the current commercial uh, applications, especially for game. Yeah, the UV mapping uh, assigns a two-dimensional texture coordinate u and v to each location on the mesh XYZ. So during rendering, the texture is sampled using these coordinates. So we can cut and flatten the surface into a 2D map and paint it there and transfer the color back to the 3D object. But mesh can be a very good representation to render, but mesh is hard to edit it because changing vertex position for the mesh will deform a mesh. Yeah, it's hard to preserve its connectivity. So meshes are memory efficient, explicit representation. The surface deform naturally and support texture mapping. Their main limitations is that the topology. Yeah, learning usually requires a template, a parametric family, because the mesh is hard to use in the convolution network or transform. Because like for images, it will have fixed size, but for meshes, an object can be represented by like one vertex size or 1,000 faces, but actually they will be represented the same shape. So for the current deep learning technologies, if the mesh cannot always have a fixed point clouds or fixed number of the vertices, the convolution network or the transformer is quite hard to process the mesh. Another more friendly representation for the deep learning technology should be the voxel representation. It quite be easy to understand, like image is a 2D array, so the voxel representation is a 3D array. It will be the W by H by D grade. Yeah. So most of the deep learning technologies like convolution networks or the transformers can friendly to operate the voxel grid, like the maybe we can call it cube. So the voxel grids are generic. So the same this structure can replicate objects with different topologies, multiple components. Yeah. But the most important limitation is that the resolution is important. Yeah. Here is example. If we want to exactly store the accurate surface or the shape of the object, we have to use a high resolution. But for image, we can use like a 4K resolution. But for the cube, if we use a large resolution, the voxel number will be quite huge, and it will be a quite difficulty computation burden for the current deep learning technologies. And the voxel representation is will be quite easy to process with 3D convolutions and 3D transformers to predict occupancy. The occupancy network or occupancy prediction, this task is quite important, especially for robotic related tasks or the autonomous driving. Like the Tesla introduced the voxel prediction task in 5 years ago. Yeah, because we know the Tesla, its self-driving system is very powerful. Yeah, one key technology is the occupancy prediction, because in the past of self-driving systems, how it works, it will be a multiple component system. Like first, it will use a segmentation network to segment like human beings or the cars or something else, and the system will detect the bounding box and feed the bounding box into a planning system. So the first round self-driving system will be a totally white box system. Yeah, but the main limitation is that if the perception network cannot recognize what the type of the object, will miss the object, right? Yeah, if there is a object unseen from the category, so the segmentation network cannot decide which category the object is. So it will miss the object. So the planning system will miss the object. So it will be quite dangerous. So Tesla first introduced the occupancy prediction network is that we do not to determine which object it is. We only to determine whether the voxel space is occupied or not. Yeah. So we do not to distinguish the object is a dog or cat or anything else. We just to know the voxel of the 3D space is occupied or not. So the question will be quite easy. Yeah. If the space is occupied, it means that the car cannot to go straight. You're right. We should do brake. So the occupancy prediction, this topic also is very famous, especially in the past 5 years. Another important idea to represent the 3D space, 3D is a parametric surface. Yeah, this idea is also easy to understand. Yeah, because we can use mathematical function to represent a sphere or a triangle, right? So in that case, we also can use mathematical function to represent a surface. Like maybe you can use high-dimensional functions to represent a complex surface. Usually we call it manifold. Yeah. Here is an example of the parametric surface. It has many beautiful properties. Yeah. First is that the representation, the parametric surface is fully differentiable because it's a mathematical function. Yeah. So the idea is quite the the idea quite inspires the differentiable rendering technology development. If you know the nerve or the ground splatting or the news, like the neural surface rendering technologies, it's quite uh, associated with the parametric surface. Yeah, because we can use network to fit a parametric surface. Yeah, because current deep learning tools, we know that we can use like TensorFlow or PyTorch to easy to calculate the gradients of a network. So if we use a network to represent the parametric surface, it can be very easy to use it. Yeah. So we can to store an image into a network or store a video into an image. Also, we can store a 3D surface into the network, and we can calculate its gradient. Yeah, here is an example of the parametric surface. Yeah, we can use a network to represent a shape of the different animals. Yeah, here is an example that we can first we can use a network to initialize a sphere. Right? Maybe you will know that the network is randomly initialized, but we can also to carefully to initialize the network to produce a sphere first. Yeah, then we will to like to uh, using the training process to enforce the sphere gradually become the car. The car will be our the goal. Yeah. So this topic is also important in the like the CVPR conference. Yeah, it will be correlated with like 3D shape analysis, like 3D shape segmentation, like the neural surface rendering. Yeah, if you familiar with like nerve and the news, yeah, you can to use network to represent object you would like to optimize, and you can use like a point cloud sample from the ground truth objects or use like images to provide supervision to optimize the shape. And the network will be gradually to become the shape you would like to want to achieve. So at this point, point cloud meshes and parametric surface can all describe the surface directly. Yeah, this explicit surface reputations are efficient near uh, the boundary, and they do not naturally answer questions throughout the surrounding volumes and topology. So both grids and implicit functions and take a different viewpoint. They define values throughout the three-dimensional space, and these volume-based reputations make occupancy and topology changes easier. Yeah, although they may require more computation away from the actual surface. Yeah, because if we would like to represent a safe surface, we can only to store like the point or the surface in the space. But for the voxel or the cube, we have to also store many uh, not occupied voxels, right? So it also will be require lots of memory and the computation resources. Like the implicit surface is uh, defined as a level side of a scalar function. Yeah, just just now we mentioned the parametric surface that we can use explicit mathematical function to represent the surface, but in many cases we cannot to uh, explicitly define a function. Yeah, we can define an implicit surface that called like we define a function and we enforce the zero level side should be a surface. Yeah. Yeah, here is some examples of implicit surface. Sine distance function is maybe maybe it is the most hot implicit service. Yeah, sign distance function, like its name, is store the sign distance. It will measure. Here is an example. Sign distance function, the that we can every we can send like XYZ point into the function, and we can calculate its value. If its value is 0, it means that this at point, the input point, should be on the surface. If its value is 1, it means that the point to is near a surface, the distance is 1. Yeah. So we can use the sign this function to decide which is the inside and which is the outside and where is the surface. And more importantly, the implicit surface, it has unlimited resolution. Yeah, so we can use that idea to represent a quite large thing. Yeah, but the limitation is that if you would like to know what's the 3D is, you have to send many samples of 3 words to check its value. Yeah. Yeah. In the deep learning area, if we would like to use a network to represent the surface to store the scientist function, we will also to enforce the norm of its gradient to be unit. Yeah. It will be quite interesting. If you are interested, you can to search the answer after the course. Yeah, this is a quite popular, quite smart way. Yeah, if you are interested, you can search a paper called the positional encoding. Yeah, for the network, if we to enforce the norm of gradient to be unit, we can to enforce the scientist function represented by the network can be smooth. Yeah. So it can to represent a quite clear surface. Also, we call that the uniform constraint called econo constraint. Yeah. So the goal is that we can enforce the gradient magnitude is 1. This structure supports efficient sphere tracing and provide useful regularization when learning neural implicit surfaces. Okay, the time is almost near the. Any questions? Yeah. Okay, thank you guys. If you. Okay.
Can you think about like further perspective of this area, kind of like how it will be integrated with LLMs and what LLMs can and cannot do in this 3D modeling?
Sorry, not.
Okay, I will try one more time. So, how good are LLMs right now at modeling things like this? And what do you think about multimodal models that on one side LLMs and on other side consider this specific or less specific approaches to 3D modeling?
You say biologically.
Maybe.
Okay, so so the 3D vision is quite important because the human beings use the 2 eyes to perceive the world, right? Yeah. In many studies, like it calls like the biologically vision. Yeah, it will consume most of energy of our brain. Yeah, so I think like for the robots or NEC applications, will be also need the 3D vision technologies.
Okay, thank you a lot, and thank you for the lecture.
Okay.